of the time up on Mauna Kea, okay. This is what you would see as we're getting ready to go on the sky. And Jen, actually, this might be a good opportunity for you to describe a little bit about what happens as soon as we start opening up the dome and doing things like tuning the primary mirror and whatnot. Would you like to maybe talk a little bit more about that?
Sure. So we have air conditioning units located inside of the dome, which run all day, so that the inside of the dome, and it's about 0 degrees Celsius. We like to keep the dome because that's usually the temperature of Mauna Kea at night. So when we open the dome, it doesn't take long for the temperature to equalize. So what happens is we'll start opening usually about 30 minutes before the sun sets, so that the air has a chance to settle and the instruments have a chance to, it's better when everything's the same temperature. And also the air over the mirror doesn't have eddies. So we try to control that with the vent gates, which are located on the sides. So during the night, depending on which way the wind is coming, we'll open or close one of them slightly more or less than the other, so we can control the dome seeing. But what Peter was talking about in the beginning of the night, we would tune the telescope, but we haven't been doing that. We used to do that with Altair, but we're not using Altair right now. So basically, everything's been great. We basically go to a standard star, and we will get a seeing measurement and let the focus and astigmatism settle. And yeah, that's what we do at the beginning of the night and throughout the night, controlling the dome seeing.
Okay, great. Thanks, Jen. If you look down at the bottom of the telescope there, it's a little bit kind of in the shadows there and a little dark, but if you look carefully, you'll see down there some boxes and some little cylinder-like thing, a whole bunch of stuff mounted on the bottom of the telescope. Well, all of those those boxes and whatnot, those are the instruments that collect the light, basically. It's imagers, spectrographs, adaptive optics systems, those types of systems. Now, one of the things that makes Gemini quite unique is that, thank you, Andy, for the arrow. That's that's a nice touch. One of the things that makes Gemini quite unique is that we can switch between those instruments on very short notice. And so that allows us to operate in a mode that that we refer to as queue scheduling, where we get the requests from the principal investigators, the researchers using Gemini, astronomers literally from around the world. They will send in a proposal. It will get reviewed by the time allocation committee, and then it will go into the queue. And once it's in the queue, then we take a look at the sky conditions, where things are in the sky, what instruments we're using that particular night, and we'll schedule those observations for the astronomer. If things don't work out, the weather conditions change, or for whatever reason we can't get that data, we'll try again another night. In the old days, astronomers would come to the facility and be, in a lot of cases, just luck whether or not the conditions are right for what they wanted to observe. And most of the time they get their data, but not all the time. With this mode that we use, queue scheduling, it essentially guarantees if you've got a highly ranked program, you're going to get data, and it's going to be really good data that will be will match the conditions that you need for that observation. I don't know, does Jen or Andy, anything else you want to add to that that topic?
I guess I would throw in that conditions means a number of things. So cloud cover, water vapor content in the upper atmosphere, seeing. So all of those things are known to our database. And when we select observations, we know that they'll be compatible with what the sky is giving us. So I don't think it's a bad thing to be showing pictures of Gemini with clouds overhead, because clouds don't worry us as they would have in classical scheduling.
Yeah, we have the Q plan in different variants for any given night. So we have, depending on what the conditions are like, we might have to abandon if thicker clouds come in and a program has, you know, requirements of it being photometric. So that we'll have to move to, you know, a CC 70 or 80 plan, maybe any. As long as we can guide, we're good. Pretty much, as long as the program can handle it.
Okay, thanks, Jen. Great, great. Benoit, just a quick question. Terms like seeing, is that something students are familiar with, or should I explain some of those terms?
Yeah, so we've been introducing the seeing condition in the past days. I hope it should be clear for everybody. But I mean, it's always good to repeat some of the concepts. So please feel free to describe how is how good is the seeing in Hawaii as well.
Yeah, so when astronomers use the term seeing, they're talking basically about a lack of turbulence in the atmosphere, stability in the atmosphere, the turbulence that would distort our view of space, basically. And I'll talk a little bit more about that in a few moments. This is just a pretty picture I wanted to show you here that shows the dome. This is our cloaking technology at Gemini, where we make the dome disappear. Actually, the way this image was obtained was we took a long exposure and just rotated the dome with a very dim light on inside the telescope, and took this picture with the Milky Way. So you can see the telescope in there as if half of the dome is missing, but it was just a photographic trick to do that. Okay, I'd like to show you now some of the types of things that we observe with the Gemini telescopes. And in particular, I want to show you some observations that we've made using adaptive optics. And again, I'm sure you're familiar with this, but basically adaptive optics is a technology that allows us to cancel out a lot of the turbulence in the atmosphere and take out those distortions caused by air of different temperature mixing together in the atmosphere or turbulence. And this is, of course, Saturn. If anybody's gotten out over the past month or so, Saturn is quite prominent in the evening sky. And you can get some really nice views of Saturn and Jupiter, and now Mars too. But this is using the Gemini telescope and adaptive optics. And if you look down at about the 7 o'clock position, maybe 6:30, you'll see a disk down there, and that is Saturn's moon Titan. And to be able to see the disk of a moon like that in this image is quite phenomenal. The resolution is quite remarkable using adaptive optics, but we can zoom in even closer and take a look at Titan. And when we do this, this was actually during a time when there was a storm in the clouds of Titan, and that's what that bright spot is. And so we can use this technology, adaptive optics, to monitor the weather on moons of other planets, which I think is just remarkable. But when I was a kid, one of the first things when I first started getting interested in astronomy is I had a 6-inch telescope and looked at Saturn, and just blown away by how beautiful it looks. But Titan was just a little pinpoint of light. You couldn't see any more than just a pinpoint of light. But now with large telescopes and these technologies, we can actually see weather in the clouds, which I think is just remarkable. Let me give you a little background here. I'm sure that you probably already learned a lot of this in class, but I want to talk about something called wavefront optics, which is, if you're looking at an object with light coming in from space, the light will come in parallel rays. The artist in this case sort of took a little license and curved them a little bit, but those light rays coming in will be straight and parallel and completely undistorted, flat. However, when they reach the Earth's atmosphere, which is about the middle of this illustration here, those wave fronts are going to interact with the atmosphere. And what happens is that you get cooler air mixing with warmer air. The warm air is less dense, the cool air is denser. And so the index of refraction, or the amount that the light is bent, is different depending on the density of the air. And you have all this air mixing together all the time. But if you took a snapshot, what you would see, if you could see that wavefront, you'd see that it was no longer flat. it's coming in and it's distorted by that turbulence in the Earth's atmosphere, that warm air mixing with cold air. Same thing you feel in an airplane when you're flying in an airplane, bumping along because of more dense and less dense air, basically. So how do we address that in astronomy? Well, we're using a technology called adaptive optics, and one of the jokes I like to make is that there's not enough stars in the sky for astronomers. In order to use adaptive optics, you need to have a fairly bright star, a relatively bright star, close to the object you're looking at. And so we can do that by making what we call a laser guide star. And so what's going to happen here is you can see that yellow box up there, that's our stylized laser, is going to propagate a laser beam through some optics on the side of the telescope. And you can see the dome is now open, and we're going to see the laser beam here go up through the optics and then launch from the top of the telescope, behind the secondary mirror of the telescope. Now we're going to zoom up away from the telescope about 90 kilometers up. There is a layer, very thin layer of sodium atoms that get excited by this laser. This laser is a sodium laser, yellow-orange laser. And it excites the sodium atoms up there. And when we look at it from the perspective of the telescope, we don't see a column of light, we see a pinpoint of light, okay? An artificial star above the turbulence that is disrupting the light. So that light from that artificial star comes back down through the telescope, and we focus it, and we can use that light to sample what the atmosphere is doing to that starlight and the object that we want to study. And so back here at the back of the telescope, where all the instruments are, we have a adaptive optics module here, sort of a generic adaptive optics module in this case. And so we're going to cut away and take a look at what happens to that light that's being focused by the telescope. So the light comes in, and it goes through what's called a collimator and over to a deformable mirror, a beam splitter, and then the longer wavelength light comes down to a detector, and we're going to see what that detector in the center shows us. And it shows us a star that's undulating and moving and just all blurry. So let's fix that. So what we're going to see here is the light's going to come in from the upper left, and you see how it looks like potato chips? Okay, it's all distorted. Well, it hits a deformable mirror, and then some of the light goes down, and it's split by this thing called a beam splitter. And then we have a wavefront sensor that looks at that, analyzes it, and makes the same shape, but half the amplitude on that mirror, so that when the light reflects off that mirror, it's nice and flat, just like it was when it came from space. Not exactly, but very, very close. And then when it focuses on the detector, we go from that blurry star image to a nice sharp image. Does that make sense? Or Benoit, do you want to add anything to that, or any comments?
I think it's pretty clear, and hopefully everybody now is familiar with the concept as well.
Okay. This is just a pretty picture here that we obtained showing the laser propagating in the sky for one complete night. Over on the left, you can see the moon setting over there, but you can also see the glow of evening twilight on the left horizon. And then way over on the right, you can see the morning twilight. So this is one complete night. I got a trivia question for you, and I think it's a pretty easy question. What direction are we looking at here? Do you want to venture a guess? I'm sure you know, it's that you're just being shy, right?
I see someone
looking.
Someone says west here.
Well, no, yeah. Well, the west is over to the left side of the image, yeah.
Oh, we have the
east. What's that?
Someone says north, the polar star.
Very good. Yes, yes, you can see Polaris, the North Star, making a very small circle. A lot of people think the North Star is directly over the Earth's North Pole. It's about 1/2 degree off. There's no reason it should be exactly over the North Pole. It's just chance that it happens to lie there right now. But yeah, we're looking at the North Star. By the way, the Hawaiian name for the North Star is Hokupa'a. Hoku means star in Hawaiian, and Pa'a means unmoving or stationary star, because it's mostly unmoving. It stays in essentially the same place all night. So anyway, this is the laser propagating, sort of scanning through the sky as the night goes by, is what we're looking at in this image. Okay, everybody familiar with the constellation of Orion? You get a nice view of it here. Those 3 stars in a row, if you go down and a little to the right, you'll see a little fuzzy reddish thing down there. Anybody know what that is? You can see it with a pair of binoculars. It's a star-forming cloud called the Orion Nebula, or M42. Zoom in a little bit more. And we'll go and we'll take a look at a few more views of this. I think that's a Hubble Space Telescope image. And now we're going to take Gemini and use adaptive optics to zoom in on the very core of this star-forming region. Down in the lower left of this image, you can see it's kind of bluish and hazy. Those are some very massive stars that are being formed in this, this stellar nursery. And star birth is a very messy process. And so what we're looking at here is a very, very small section of the Orion Nebula. We're going to zoom in a little bit more. And if you look over towards the right of this image here, you'll see that there's like these pillars that come up and look like they're sort of spreading outward from that lower region there. And you'll see at the tip of some of those little pillars there, some little blue dots up there. Can you see those pillars with the blue dots? Okay, well, what's happening here is that those blue dots are clouds of gas that contain iron, and they're referred to sometimes as the Orion bullets. And they're moving out at extremely fast speeds and causing the neutral hydrogen, which normally doesn't glow, to heat up and glow. And that's what those pillars are. They're kind of like tracers on a bullet. If you've ever seen a movie where they show the path of a bullet through air, sort of a stylized thing. But this is really looking at that material that's being blown out from the formation of those stars and exciting the hydrogen as it passes through it and causing it to glow, making these tracers or these pillars in this star forming region of Orion. And because of adaptive optics, we can look at this and then maybe 5 years later look at it again, and the resolution is so good that we can see how much these bullets have moved over that amount of time and start to infer something about their velocity and what's happening down there in that star forming region. So this is one of my favorite adaptive optics images that we've obtained with Gemini. The detail is just phenomenal, and it's in an object that is quite accessible. If you have a small telescope, you can see the Orion Nebula. You won't see this, but you can see it's quite easy to see even in a pair of binoculars if you haven't tried that. This is an image that was just released on Monday. This is an object called the Carina Nebula in the southern hemisphere. So if you're an amateur astronomer in the southern hemisphere, this would be a showpiece that you'd look at quite frequently. But we looked at it with the Gemini South Adaptive Optics Imager, and this is an image that was obtained of this particular, the western wall of the Carina Nebula, which is a great example of just the clarity that we can get. And Benoit, you hadn't seen this one before?
No, I think it's the first time I see it. It's amazing. It's better than the HST images that we used to see.
We think so, yeah. So, I mean, with this technology, we can rival the view from space. I mean, and especially when you consider that, you know, Hubble is a 2.4 meter telescope. Gemini is an 8.1 meter. So we collect a lot more light, and under ideal conditions can theoretically observe even more detail than the Hubble Space Telescope can, depending on the circumstances. So, okay.
Just wanted to shout out to Benoit there. This is GEMS. This is the system that Benoit worked so hard on, and it's fantastic.
Yeah, Benoit, if you have any gray hair, that might explain how you got the gray hair. system, right?
I spent some time at the summit doing the integration and commissioning of that. And actually, the Orion images, I remember very well when we get the first images, and we were really amazed by those fantastic images. And I believe the Orion image that you showed previously, it's probably one of the biggest AO image in a few shots that people have been getting. So it's a really wonderful image. Yeah.
Yeah, so you can see that this is a mosaic of what, 3 or 4 images, I think, all together into one.
Yes, it's three pointings and a couple of filters. But the new one is even better. The Carina Nebula, it's fantastic. Yeah.
Yeah, we were quite pleased with the way this data looked when they finished working on it. So. This is not using adaptive optics, but this is some of the other types of things that we study. These are some interacting galaxies, galaxies do these dances in space oftentimes, and over millions of years. If you could watch it, you could see these two galaxies orbiting each other. One of the things that happens when galaxies interact like this is it will spark star formation. And you can see in the top spiral here, especially, those red clouds. Those are the clouds of hydrogen, mostly hydrogen gas, coalescing together to form new stars and star clusters. And so there's a lot of activity going on in this galaxy, quite likely spurred by the interaction with this other galaxy. So, and the last image of data that I want to show you from Gemini, this is Jupiter. I know it doesn't look, it looks kind of odd for most people's views of Jupiter. This is an infrared image of Jupiter. And this was part of a program combining data with Hubble Space Telescope and the Juno spacecraft at Jupiter. And so Hubble and Gemini made observations of the cloud features in Jupiter that would inform the Juno spacecraft to focus on certain areas, and where they were able to study lightning and the cloud characteristics and features in the clouds, and looking down deep into the clouds to understand the meteorology of Jupiter. And here's some of the data with the Gemini data and the Hubble Space Telescope data that was combined together to do that, to work with the Juno spacecraft around Jupiter. And this here illustrates a technique called lucky imaging. The way this works, and actually even amateur astronomers use this technique, is that we'll take thousands and thousands of very short exposures and then take the sharpest of them when the atmosphere was especially crisp. And so let's see, I think this movie, wait a minute, let's see if I can make this play. There we go. And so you can see how the atmosphere the turbulence is changing all the time, but every once in a while you get these really sharp views of the planet. And if you take just those sharpest views when the atmosphere was really behaving itself, put them all together, that's what you get on the right in that first image that I was just showing you, called lucky imaging. And if anybody's been out looking at any of the beautiful planets in the evening sky through a telescope, you know that you look at the planet for, maybe for several minutes. And over that time, you'll see the atmosphere get less turbulent, more turbulent, less turbulent. When it's less turbulent, all of these details can just jump into view. And so that's what we're doing here, is using Gemini and what's called lucky imaging to take those moments of really good, crisp views and put them together into one image. And with that, I have finished my slides. Let me turn off sharing here, I think anyway. There we go. Stop sharing. And we've got 3 minutes for questions, or actually, Jen, you also had some images you wanted to show. Sorry, I totally forgot to do that. Did you want to show some images that you've done with the cloud camera over the years?
Sure. So I'll just say that I mentioned we went remote in 2015. So we used to work at the summit at night, but we moved down here to Hilo in November 2015. And before that happened, basically we had some weather sensors, and we used an all-sky camera that another telescope has running. But really, we didn't know if bad weather was coming until it pretty much the humidity started to go up, or we started to see clouds on the all-sky camera. But when we went remote, we got these awesome cloud cameras, so we're able to see the weather coming sometimes hours in advance. Sometimes it still happens very fast. All of a sudden, you know, there's clouds from nowhere, really. I'll just share that I just put a few videos together of some of the stills from our cloud camera. This is in a west cloud camera. This is lightning coming from the southwest. And so we know we're gonna have to close, but we stay open until, you know, until we know that we don't want harm to come to the telescope. So, but right now the weather's still okay where we are. Once it starts, you know, in a couple minutes, you know when it's gonna hit us. So we basically close the telescope. But so this is kind of this.
Jen, did you have any pictures of the sprite? Did you have any pictures of sprites that we've, oh, you do, okay, no mind.
So while I'm working at night, I'm constantly, I have eyes on so many different screens, but I do watch the cloud cameras because I want to know what's happening with the weather. This is over, this is facing south. This is the actual summit of Mauna Kea. Kilauea is over here. This is lightning happening, and then this up here is a sprite. It's caused by electric discharge. Anyway, I get to see really, really cool phenomena happen. This is more lightning. This is IRTF. Sorry, my internet's really slow, so okay, it just finally came through. This is localized lightning as well. It's kind of hard to see the detail in this cloud, but it's literally just lightning in this cloud, and that's also over Kilauea. And this is from my shift last week. It's a moonbow. This is a rainbow from the moon. So this is at night. And one more thing. So this is part of our wall display. And I saw this cool thing happening here. Also down here. So these are light pillars, and I don't think that well, anyway, I did make a movie. My internet's taking a while to load, but you can start to see them forming over Hilo, these light pillars. So it's like ice crystals inside the clouds, and the lights are causing these reflections. Try to.
Oh, that's fascinating.
Okay. Oh, and then there's some things that are not naturally occurring. Let's see if this loads. If not, I have a, oh, here we go. That's the SpaceX constellations that we can see in our cloud cameras.
Huh. Great. Thank you. Thank you very much, Jen. That's fascinating. Yeah, I've noticed when I was out with my telescope over the past few nights, I haven't been observing for quite a while, and it just seems like there's so many more satellites now that you can see in the field of view. Just when I'm looking at a particular object, you know, more times than not, I'd see a satellite pass through. So that is an issue for us.
More and more. Yeah. I saw a question about airglow. Yeah, we can see a lot of airglow, especially in our cameras. And oh, Andy answered that question. Also, another phenomenon in the picture behind me is this is Mauna Kea as seen from right outside of the Gemini telescope, Gemini North telescope. It's a glory. So the sun is just making this rainbow. It's at sunset. And if I zoomed in more, you could actually see my shadow as well as the
sharing. Jen, you're not sharing?
Oh, I just mean in my virtual, my picture behind me.
Oh, your picture, right.
Yeah.
Oh, sorry, I'll have to zoom in a bit.
It looks like we've got quite a few comments in the chat and probably some questions in there. I can go longer. I don't know what your schedule's like, but happy to answer as many questions as we can. Jamika, you want to lead that?
Absolutely. Okay, so we had a question a little bit earlier, and I sent it in the chat. I don't think we quite saw it. So thank you for question time right now. Peter, you were showing us earlier some interacting galaxies, and Andy and I were trying to figure out which galaxies those were. Someone in the chat mentioned that they missed the name you said, and I didn't remember.
Oh boy, I don't remember the name. It is a press release. I can certainly find that out. I don't remember the NGC number on that. On those.
Yeah, I was a co-I on that, and the name is escaping me right now. I think.
Yeah, I don't know if it has a common name too, but it's obviously it's a what's called a New General Catalog or NGC number. I can certainly look that up.
Okay, Andy thought it was NGC 6872, and here is the link.
Oh, good. Okay, yeah, go ahead and put that in the.
There is an NGC. Oh wait, maybe that's not it. NGC.
Were there other questions?
Yeah, I will go down the line here. So Jen was showing the awesome video with the constellation satellites. And so the question here is, do SpaceX satellites disturb your observing a lot?
Currently, maybe not as much as it probably will in the future. But I'm pretty sure it will, the more satellites that are launched, it will probably affect the data.
Yeah, there are quite a lot of studies being done about the impact and how to mitigate it. And I know that the satellite companies are also working with astronomers to try to bring the reflectance down and the infrared emissions and all of those sorts of things. But the bottom line is that it's going to be a problem. And so we can try to minimize it, but it's not going away, unfortunately. And it's probably going to get a lot worse before it gets, well, never going to get any better.
I think at the moment, it's not a huge problem for us. I mean, our largest field of view is like 5 arc minutes or something, and it's not going to get much bigger than that. Some of the wider field telescopes like Subaru, they'll be seeing them all the time, particularly when some of the higher constellations get launched, like the Samsung one, which is way, way higher than this. So.
Yeah, especially I think it's anything above what 600 miles begins to really be a problem because it can be visible most of the night. If you're familiar with the Rubin Observatory, which is a huge survey instrument, it has a tremendously wide field of view, and it's going to have satellites in every single image that they'll have to deal with. And they're looking for transient events or changing events in the sky. And so things like satellites can be very disruptive to that. So yeah, there's a lot of work being done right now to try to mitigate this and overcome the light of satellites.
Okay, our next question is, what are the plans for Gemini after the new generation of telescopes?
I think Andy's the perfect person to talk about that.
So do you mean after the things like the TMT and the GMT? I guess that's the question, right? So I think we've been through this once before. I mean, I used to manage UCURT, which is just next door on the mountaintop here. And when the 8-meter telescopes came along, we repurposed UCURT to do something else, to do something that was complementary. We did sky surveys, and we also retained the ability to do general purpose observing on objects that were too bright for 8 meters. And there's a lot of sky out there, which needs to be observed. So I think Gemini has its own particular strengths. Infrared is one of them. Almost every image you've seen here has been infrared in one way or another. And so I think a lot of general purpose astronomy will carry on. And we're looking at, certainly in Gemini South, which is right next to the Rubin telescope, we're looking to be very, very productive in following up the large survey of space and time that the Rubin Observatory will carry out. So there's an awful lot to do, and that won't change with the large telescopes coming online.
It may change the type, some of the types of things that we observe and whatnot, but we'll be busier than ever.
Okay, our next question. Oh, in the chat, I dropped a link to one of our live from NOIRLab at Kitt Peak or at Arizona episodes where we interviewed Dr. Constance Walker about the Satellite Constellation Network. She is a part of the team working with the group in general on addressing those issues. So that is down in the chat. Okay, so our next question, we have a statement and a question. So the two Gemini telescopes have some overlap with respect to sky coverage. Have they ever been used to do parallax measurements of close objects within the solar system, probably? And the follow-up question with that is, or any other observations where they observe the same object simultaneously?
Parallax, no, that I'm aware of. Sorry to disappoint you on that, but it does sound fairly intriguing. But I think there are more technical issues to doing that than otherwise. But there have been instances, though, where we've observed the same object with both telescopes, and we also get better time coverage too. So if something is changing rapidly, we can continue on with the other telescope. However, that doesn't happen frequently. Andy, what do you recall any instances that we can give as an example on something like that?
Not of genuinely simultaneous observations, although we certainly wouldn't rule it out. And we're in the process of rewriting all of our software to make the two telescopes much more coordinated than they are. Things have changed in however long it's been since they were built, and the internet is now much more reliable. So we intend to do more coordinated observing, particularly with the Rubin telescope. And we'll be transferring objects from south to north in the course of the night. And I should probably say from east to west, because it's longitude coverage that matters when you're doing the time domain.
Great, thanks, Andy.
Thank you, Andy. So another question is, how many days of winter do you lose to observe? How many days of winter observation do you lose because of clouds? And I guess that can just be observations in general. How many days do we lose due to cloud coverage?
I think we're on the sky, what, about 80% of the time? Is that an accurate number?
Yeah, but so in Chile, things are much more reliable. The winter is awful, and we lose something like 40% of the time through the winter months. Maybe a bit more on some years. In the north, it's much more variable as we get La Nina and El Nino. They're different styles of winter. I don't think we often lose much more than 30% of winter nights in the north.
There can be spells, though. I'm sorry.
I was just saying, Jen probably has a better feel than I do for this.
Yeah, it's variable in Hawaii, and it can snow in July. It pretty much snows in July every year, and then the front page of the newspaper is like, oh my God, it snowed in July, and it does it every year. But yeah, it depends on, like Andy said, El Nino, La Nina years. I think climate change. I think that things are different. I've been here for over 10 years, and the weather has never been the same on any given year.
There are times in the winter in Hawaii where, Andy, what is it? We've had, what, a month of almost no observations at times, but it's not frequent, but it does happen that we'll get stuck in a weather pattern that just won't quit.
I think 2 years ago is especially bad. It was like 2 or 3 years ago. We lost several months. I'm not saying to clouds, just storms. Clouds we can power through. If there's enough programs that take thick clouds, we can just keep going. But it's the humidity and precipitation. Those are the major, things that stop us.
Mauna Kea is served by a really good forecasting and weather service run by the university. In a meeting a few days ago, the head of that group said that we should expect a really, really wet winter this time. After October is over, and October is going to be nice, he said, buckle up because it's going to get wet and snowy.
Oh. We've got, actually, Andy and I have another meeting we've got to go to in 1 minute. I noticed that there's one more question here, though, about the eruptions threatening the installation. And you said, okay, so the eruptions are not a problem, but seismic activity and tectonic movements, that's another interesting one, too, because the Pacific plate is moving at about the speed that a fingernail grows across the Pacific. And so that, but in terms of seismic activity, yes, we get, both sites get some pretty good shakings from earthquakes. And we had one, what year was the earthquake in? Do you remember, Andy, where we lost the top end of the telescope for quite a while? 2007?
Is that right? I wasn't here.
2006, I think.
2006, okay.
Yeah.
So
yeah, we do have, go ahead.
No, you go. Right.
Oh, but basically that particular earthquake shook the telescope and broke a glass rod that was in the top of the telescope. It had to be replaced, and many of the telescopes up on Mauna Kea had more serious problems than that, where the telescope actually kind of shook off its mounting and got offset on its mounting and things like that. We have restraints that will minimize that sort of thing at Gemini, but yeah, when things start shaking like that, you're going to have trouble. So yeah, we do have trouble at both sites due to seismic activity, no question about it.
A couple years ago when the lava was flowing, we did close one morning because of some ash that we saw, kind of an explosion in one of our cloud cameras, and sensors were put at the summit to measure. I don't remember, Andy, do you know what kind of sensors they were? A couple of the telescopes had them. We were monitoring to make sure that we could.
I think they were aerosol and particulates, right? Particulate measuring.
Is that what you're talking about? Yeah, we can measure things like sulfur dioxide.
The sulfur dioxide.
Yeah.
Just to protect.
Okay, Andy, we're going to be late for the.
No, I'm sorry. Yes, I have to go.
Thank you,
Okay,
everyone, for being here with us. Thank you, Andy. Thank you, Peter, especially Jen. Thank you so much. Benoit, thank you so much for having us speak to your students. If there are any more questions, please feel free to email me. Everyone has my email address, and I'll be sure to get it to the right people. Have a fantastic evening, everyone, and thank you again.
Thank you very much.
Thanks, Jamaica.
Aloha.